Go to Italian when we need to.
Yeah. Okay, this is the first. I think everybody's picked a project topic by now. Amber, I'll get back to you. Okay, I haven't had a chance to look into that. Is everybody clear about what I expect from the project? Because again, they're pretty easygoing with assignments and stuff like that. Oh, you know what, you're gonna get a whole bunch of marks. Okay. For the project, I want some good work. Okay, so let's be clear about what it should be. So here's what I would suggest. Once you have a topic that is somehow based on some existing work, right? So you have some problem that you're trying to model and simulate. So describe the system, describe the problem, describe why it's important, all that kind of introduction stuff, right? So for example, let's say I'm going to look at new technologies for sorting DNA by size. Okay, so I can talk about why you would want to do this, why you want to sort polymers by size, why specifically you might want to sort DNA by size. Okay, for example, it's in traditional methods of sequencing DNA, you need to sort the strands by size. Cool. Okay. Then talk about existing things, so like gel electrophoresis. Let's say my project, I want to model gel electrophoresis. And so I can look at work of modeling gel electrophoresis, for example, by Slater. And I can look up these papers and I can do simulations that reproduce the simple models and show that I get results consistent with those results, okay? So what I would do is base your work on some known body of work. So a couple papers that help start a field. Cool. Collective motion. You have the bid check stuff, right? This can be review papers as well, but make sure you go back to the original work and show that you can create those models and get those same results. Are we all on the same page on that? Okay.
So, if you were doing this for an actual paper, you go through and like exhaustively research the literature.
So this isn't really this isn't a paper.
Right.
Right. So are you saying do we have to do a full lit review? Or
so we can truncate the lit review.
We can truncate the lit review. Yes. But have enough so that you understand your problem, the context of your problem, and what's been done, and why you're going to go about it the way you're going about it. Okay. There might be other ways of going about it. And those might be really obvious questions. Why do you do this? And that'll come up during your talk. If you can't answer them, then it's obviously your review was a little too shallow. Right. Okay, you don't necessarily have to say, well, you could also do this and then show all the work you did on that. But at least know enough context that you can address things like that. Okay? But let's say that again. So what I expect you to do is the first part should be, well, the first part is the introduction. The first part of your actual research is to reproduce known results. Okay? I don't want you to come to me and say, I have modeled quantum gravity. Okay, and here it is. Awesome, eh? Where's my A? Okay, no, it's not going to work that way, okay? First, I want you to show that you can basically enact existing models, get known results. Because what I want you to do is not develop a model out of nowhere that none of us can evaluate, right? Get the known results, make sure you understand the known results, okay? Gel electrophoresis. What are the mechanisms for why short polymers come through fastest? Well, you get these hooking events. The time it takes to unhook depends on how long your polymer is. Okay? Okay, I understand that. Okay? We reproduce known results. Now I'm going to have my own idea. Okay? I'm going to replace the gel with a series of nanopores. Okay? And now I can build off of that model and say, okay, I'll get rid of what I was using to model the gel, and instead I'm going to do it with this. And then I can repeat similar analysis to see, does it work? Does it work better? Less efficient, all this kind of stuff, okay? So again, it's going to be in the context of stuff we already know. I want you to be creative and explore and come up with different ideas, right? Maybe extend the model, like, well, this model didn't have this in it, okay? So that model of gel electrophoresis didn't have hydrodynamics in it. I have a very simple way of including hydrodynamics, okay? That's also a good idea, okay? But it's got to start from this point so we can evaluate what we get. Cool? All cool on that, okay? And so that's what I expect out of your project, and then your conclusions, right? Whatever.
So extending the model is sufficient modification. Like adding something in.
Sufficient extension of the model is sufficient modification.
Sure. Okay, so
If you have doubts, come and talk to me because we're kind of, yeah. But I don't want to just say extending the model because you could do something really trivial.
yeah.
Right? Oh, I did it with periodic boundary conditions instead of walls. Okay, well, all right. Right? Yeah. Cool. So I want you to research something. I want you to kind of reproduce stuff, and then I want you to do your own stuff. So roughly it breaks down a third. Cool. I think that's fair. I want you to learn about some problem. I want you to learn about what others have done, but remember this course is mostly about you playing with the computer to try and solve something. Okay, and that's why that last third is so cool. Yeah?
And one thing to note is even if we try something and say it doesn't work, we can still like be like, this is what we've done, this is how we set it up, and this is
Well, this is something you learned as a
negative
grad
result.
student. When you come to a group meeting and something hasn't worked, is it okay to just sit there and go, it didn't work?
No, like
you have to
obviously
go, okay, it didn't work, so
here's
this is what I
why.
wanted to try, but this is what happened, there was this problem, right? So,
yeah, like we wouldn't just say it didn't work. Yeah, like we would be like, here's what we've been along for, like here's what we tried, here's what here's why it was breaking, whatever happened.
exactly.
Yeah.
But try and get a positive result.
Oh, yeah.
Okay, so don't just have one idea, and if it doesn't work, just describe why it didn't work and wash your hands of it.
Yeah.
Okay? Think of a different idea. So based on what didn't work, what did you try next? Okay? And include that in your report. What you tried, what didn't work, and what that led you to. A lot of you did that. I gotta say, the assignment of sorting DNA with nanopores, or sorting rods with nanopores was awesome. You guys did a great job. Very good. And that's exactly what you guys did. I tried this, and this didn't work for this reason, so instead I tried it this way, and I gave better results, but I thought I could optimize it by doing this, and that even gave better results. Cool? So fantastic. Good work. Only thing I would say there, very few people included quantitative assessment of this. Okay, there were some movies, there was a lot of pictures, but there weren't many plots of like mobility versus rod, right? Or just how far did the short rods go in some time? How far did the big rods go? Okay, that's a quantitative assessment of the sorting. Cool? I did say it at one point, for sure. No, I totally did. I remember saying it a couple of times in class and in the lab as well. Yeah. Okay. So if you want to show something sorts, pictures and movies are totally great, but ultimately we need plots. Okay. In many ways, being a grad student is it's like the search for plots. You have to find the magic graphs that fit into your research project. And when you find those magic graphs, you've done the work. Okay? In a very shorthand way. Okay? Same when you write papers, okay? This is the advice I give to my students. Don't start a paper with the abstract. Don't start with the introduction. Okay? You can start with method, because you can actually do that months before you have any results. Okay? When you have results and you're starting to write the paper in earnest, start with the plot. Write around the plot. Put your plots in there. Say, okay, well, this is the first plot I generated. This shows this and this. From this, we learned this, which suggests that we should then look at this. Figure 2 shows the thing that we can look at. Okay? Cool? The beans were all good projects? Okay. The topic today, moving on from zombies, is cellular automata. Okay, now in many ways, this is similar to what we've been talking about, but there's some differences as well. Does anyone know what a cellular automata is? Idiots?
Like a discrete particle that has rules and
Yeah, so really what it is you can have the interpretation of particles. Okay. But really, it's some kind of grid. Typically a rectangular grid. You can also do like hexagonal if you want to be fancy. Okay? Now each square on that grid is called a cell. And each cell has a state associated with it. Okay? Often, it's binary. So let's say this. Then we have this configuration. Okay? Where the hexed ones correspond to cells that are on. Or off. Doesn't actually matter. Or they're 0, or they're 1, or they're black, or they're white. And then all the other squares are the inverse of that. So if the hexed are on, all the other ones are off. The hexed are 1, all the other ones is. The hexed are black, all the other ones are. Cool. Fair enough. So cellular automata, we always have an initial state. And then what we want to get to is the next generation. Not the Star Trek series. Okay, but basically we want to solve this at t equals t plus 1. And how do we get there? Okay, this is determined by a rule set. And what does that rule set depend on? Any ideas?
Well, it can depend on anything.
Again, but for most cellular automata, in fact, I think all cellular automata depends on
Surrounding space of
Yeah.
other cells.
their own state and the state of their neighbors. Okay? At T0. Okay? So notice cellular automata, you update everything at once. Okay? So you don't march through, you change this state, and then your next one would be this one, and then this one would look at the one you just changed. So typically in cellular automata, first thing you do in your time loop is copy current state of your system to a new matrix. And then you do all your evaluations based off of that. So you can update this matrix by referencing this one. Cool? That is a common pitfall in why programs act. Cool. Okay, so what do I mean by the neighborhood? Well, I've drawn a 2D example here. What do you guys think the neighborhood's gonna look like? 2D. It's an obvious choice for neighborhoods. What do you mean all surrounding cells?
Every cell here, I mean,
Those are all
so
surrounding.
there's the 8 surrounding.
Okay, so that's one of the neighborhoods.
You got 4 surrounding cells.
Yeah. Okay, so this would be the Moore neighborhood. And the 4 surrounding cells, the ones that are, they basically share a side, is the von Neumann. So again, notice these ideas go back to people at Los Alamos. Okay? Sorry, John von Neumann, Los Alamos National Labs.
Could you please generalize the 3D thing?
Yep. A lot of stuff is done in 2D because cellular automata are so visual. Cool. Okay. So for the Moore neighborhood, okay, I want the state of this guy at T0 plus 1 to depend on its current state, and also the current state of its neighbors. So how many cells in total do you have? 9. So how many possibilities are there? 2 to the 9. That's an awful lot of possibilities. Right?
2 to the 9 or 2 to the 8?
2 to the 9, because each cell can be either 0, 1, and you have 9 of them. The total number of combinations is 2 to the 9. Right? That's 512 possible patterns. Yeah, that's a big rule set. Okay? So even starting from this simple idea, you can get arbitrarily complex, well, not arbitrarily complex, very complex rules. Okay? We're not going to look at rules that we have 512 unique rules on our system. Okay? But it actually is a possibility.
What do you mean rule set? Like, if the one above is on and the one below is off, do something?
Yeah.
Oh, okay.
Yeah. So if this guy is in an on state, everybody else is in an off state.
Yeah.
Then the next time he's on or off.
Oh, yeah.
Okay. So
Okay.
if this guy's in on state, everyone's in off state except for this guy. Then he's on or off. That's the next time. Yes. This guy's on, right, and so on, so on, so on. So there's actually 512.
Yeah.
Okay. We're not going to do that. Okay. One other little detail. In principle, cellular automata are solved on an infinite grid. Okay? It's hard to do infinite simulations. What can we do instead? Periodic. Yeah, we can do periodic boundary conditions. Okay, they're used a lot. So this is like a semi-infinite, effectively infinite system. The other thing you can do is have different rules at the edges. Here we run into the problems that when we do that kind of thing, edge effects can have a large impact on the result. Cool?
Why would they be done infinite on infinite?
Because you want to keep just this one rule set everywhere. You don't want different rule sets.
Oh,
Which means you don't want
I
edges. Yeah. Okay. So again, this means we're often going to be doing our cellular automata simulations on a, donut. Okay? Or as mathematicians say,
We can say torus.
I'm just joking, I'm joking. Okay, let's look at our first example. Okay, and this is a great example because it actually leads in very nicely from zombies. Okay, and this is Conway's game of life. Okay, named after a mathematician.
Not familiar with this pun we got.
Okay, so we're going to use the Moore neighborhood. And we're going to have 2 states. Can anyone guess what they're going to be?
One and
Dead
two.
or alive?
Yep. Alive and dead. And here are the rules to the game of life. Okay? Our first rule. We have a live cell with less than 2 live neighboring cells. It dies. Okay? So this is like underpopulation. Density is not high enough in that region for that little colony to be sustained. Live cell with 2 or 3 live neighbors lives. Okay, that's sustainable. And you can guess the next one, live cell with greater than 3 live neighbors dies. This is overpopulation.
In a Moore system, though, if you have 9 surrounding cells, isn't 3 like a pretty small number compared to how many cells around you could be alive?
Let's see what happens. Okay, so these 3 rules kind of make sense, with the exception that perhaps these thresholds are too low. Okay?
The threshold's off, so they can change depending on
Yeah, that would be interesting. That's a game. Okay. Do project talk. Oh no, we already have it.
It's become so automatic for you. In the last
Exactly. Okay, but what's going to happen here is we're missing everything is just dying here, staying alive, right? Terminal result for this might just be death. Okay, so we also want an additional rule, okay, which is going to be dead cell. 3 live neighbors becomes live, okay, and this is like reproduction.
Is that 3 or more?
I think it's exactly 3.
Okay, that would balance it.
Yeah, no, it's exactly 3. Okay. So in Conway's game of life, you need exactly 3 cells to reproduce.
This is rated PG, right?
It depends how good your graphics card is. Okay. So there are a lot of cool patterns that you get out of this. Okay. Let's try and sketch a couple of them, and then we'll look at the source of all knowledge, Wikipedia, to see a whole bunch more. Okay. But what happens?
I mean, these are arbitrary rules. The set was studied that.
I'm just thinking some
Yeah, you can make Austin's game of life up.
I was just thinking that the live cell 3 and the dead cell 3 might have something to do with it being the square root of 9, like 9 possible cells, where that might have something to do with the rate.
You might be able to prove that.
And so these patterns are kind of coming from that. It's a nice equilibrium.
Might, I don't know.
It's pretty tricky to prove stuff. If they get a pretty in there.
Anything's gonna happen here. Everything else out here is empty, not happening.
Periodic.
No, infinite system. Just in the middle, we have this little 2x2 block.
So going off rule number 1, each like the first block, that's going to die. Second block is going to die. Third block is going to die, and
All of these are already dead.
yeah, like I'm looking at the live.
So take these to be dead and these to be alive.
Okay.
So they have 2 neighbors. Everybody has 2 neighbors. They all stay alive. Right? That's like rule 2. Well, one of us is fewer than two.
Oh, okay.
There's got two neighbors, so they say about it.
3.
They have 3 neighbors.
Oh, more neighbors, yeah.
Yeah, if they're alive, okay, and they have 3 neighbors, they all stay alive.
Okay. Rule 3 is sustained, so they don't die because they're not overpopulated.
Corners, nobody dead.
And the corners.
Right? Everybody do. So stationary.
Exactly. Okay, again here, everything outside of this is dead. Okay, only the hatched ones are alive. And what does this look like?
So you're gonna reproduce in those few squares, but then the one in the middle is going to get more than 3 neighbors.
So which are the 2 squares?
So there's a square in the middle at the top
Yeah,
that it's going to make a cell.
it's going to become alive.
Yeah.
Yeah. Okay.
Same with the bottom.
Yeah.
I'm not sure sequence of events here.
So everything happens simultaneously.
Okay.
Okay, so that's the point I made over there. Okay, that's why the first thing you do is make a copy. Current state of your system, you use that for reference.
And then the one in the middle goes away, the 2 to the side stay.
No.
Why not?
The one in the middle is two neighbors.
Doesn't it have?
Less than 2 guys.
So it's not including these ones. That were just.
So he has one neighbor on his left, one neighbor on his right. Two neighbors.
But it's not including the ones that.
No,
were
no,
just-
it's so
It's
every.
just, that's what I'm trying to say, is that when you make changes, you only ever evaluate this guy based on this.
Every.
So the first thing you do when you have your system, right? Okay, here's the state of my system. I want to evaluate and make a new state. First thing you do is copy that here, and then start changing this. And you always just look at the copy, which doesn't change. Okay?
Yeah.
So that means it's all simultaneous. Okay? So what happens to the center here?
States.
How about this guy?
You got it.
And this guy? Okay. And then what's the next state of this guy?
It's the opposite. It goes back.
Okay? So this is an oscillator. Okay?
So this is something where our initial conditions are basically going to determine what type of system we end with.
Absolutely.
So I guess we should be able to get like both deterministic and can we get chaos?
It'd be hard to measure chaos.
I guess they're all technically deterministic. If you can just keep them.
Yeah, it's all deterministic, but it's really complex.
Lightweight spaceship.
Chaos is deterministic. See, right?
Pulsar is absolutely awesome. That's so cool that you can get that pattern.
What's cool is that somebody figured out that you can get that done.
Funky, eh? So we can get stable solutions, we can get oscillators, even quite complicated ones. And we can also get what are called spaceships, okay? Which are basically oscillations that also translate.
So it's like 3 or 4 states that they travel through, but they also move.
They also translate. Cool?
I think we call them spaceships.
You can get a glider that glides into a block, and now what?
Here's another one, okay? So, before we answer Martin's informed question.
Oh yeah, life is life. You get death. That's horrible.
Look at how we would code this, okay? The top of this file has all the usual rigmarole.
Yep.
Okay, this is our header. This is our initial state. I'm going to do 2D, so I obviously got to go over I and J. Okay. Here's my main loop, my T loop. The first thing I do is copy my state to a P state, in other words, the previous state. Cool. And then when I'm calculating number of alive neighbors and stuff like that, I always refer to P state. Cool. Okay. So now I'm going to loop over every ij. And for every ij, I want to loop over its neighbors. So I want a dx that goes from -1 to 1, a dy that goes from -1 to 1. Cool? And then these are my boundary conditions, periodic. Good?
Isn't that going to hit the center like a lot of time?
Hit the center a lot of times.
So,
So dx is -1, then it's 0, then it's 1. Right?
Yeah.
And for oh no, I see. Okay, never mind.
So it hits the center once,
Yeah.
and we take that out of the loop. Okay? But we don't want it when dx and dy are equal to 0. Okay? We don't want to include that in our neighbor calculation.
Because that would be kind of what?
No, because you're trying to figure out how many of your neighbors are dead or alive. You can't look at yourself. You're not a neighbor. You are yourself. Right?
Oh yeah, you're.
You live alone in the country, you can say you have no neighbors. Oh, I have one neighbor myself. Well, unless you're Buddhist or something.
that's how crazy people start.
So then all we have to do is, so in this loop, all we're going to do is keep track of the number alive and the number dead. Okay? And then when we get down here, we evaluate, okay, if we're alive and the number of alive neighbors is less than 2, we die. If it's greater than 3, we die. Okay? If it's 2 or 3, we live, so we don't. Cool? If we are dead and number of alive neighbors exactly equals 3, we become alive. Okay? With a miracle. Okay. Cool. And so that's all there is to the program. It's very, very, very easy. Okay. In fact, we're going to deal with even easier ones. Okay. So as Austin has already put his finger on, what makes this interesting is not only the rules, but the initial conditions. Okay, so let's do a blinker. And here's the initial condition for a blinker. I just need a row of 3 cells in a row that are alive. I'm just going to set them equal to 1. Cool?
Did you write all this?
Yeah. Yeah, no, I know. That's why I haven't read your
That's why we're getting all our secondaries back next week.
Don't say that on camera. No, absolutely.
No, it's fine.
What's wrong with Rome?
Yeah.
What do you think? Oh, sorry.
ET does.
I hope this is the right one. The beam takes a while to load, so I'm actually going to do this on a really big print. Yeah.
You're probably not down.
People say it's overkill, but I say if we got a power, just processing power, use it.
How to put that back to use.
Just in case something's happening at the side of the grid.
What does a blinker do? It blinks. Okay. Hold on, blinker. You barely see. Okay. There's the little blinker. Cool, eh? Let's try a glider. Okay, and this is a spaceship. So what we expect to happen now is what?
Well,
So an oscillating pattern that also translates. All you need.
would pass through. Just eventually.
Okay. Okay, so there's my little glider. So all I'm doing is I'm starting with this pattern down here. Okay, simple pattern. And I'm just applying these rules at each successive time step. There's my spaceship. Okay, we've achieved interstellar travel.
So in practice, you're looking over all 1 million of these each time.
I sure am. Kyle.
And look how fast it does it too.
No, I know. It's impressive how fast you do.
Yeah, especially when you use C to program.
Yeah.
Not Python.
Yeah.
Not Python now.
I have.
No, I'm more trying to get Mark. I was going to go, well, you did vector.
No, for the science thing, I don't think.
No. Okay, so those are, that's my little glider and my blinker. Then there are also Methuselahs, okay, which take a very long time to die or come to a stable equilibrium. Cool. And this is why my system is so big. Let's look at two of them, Die Hard and Eagle. Die Hard because it's the best Christmas movie ever. Or so the internet tells me.
No, I don't think that's good.
Neither did Python. Because
That's
it, oh, you think?
it's always hard.
No, if you want to vectorize something like, well, I'm pretty sure a lot of it.
So in these ones, we're looking at a pattern that evolves over time and eventually. That looks like it takes over the whole system.
Spoiler alert.
Oh my god. Bruce Willis, you just took over everything.
So you're just seeing through the, you have orthographic projection?
Graphic.
Yeah.
Um,
I think you're just seeing through the gap.
yeah, but it really looks like Die Hard didn't work here. Well, there's stuff going on down there.
Is this playing?
Yeah.
Okay.
Yeah, what's happening now?
Maybe upside down.
No. I think it's just a graphics.
Oh, there it is.
It's DMD up to its usual tricks. Okay, so that's Die Hard. Okay, it's a really simple initial pattern.
There you go. Yeah.
All dead. No, that's it. Oh, all dead. When it's all dead, it's all dead. We don't get spontaneous generation. Okay. Let's try equal.
Did you ever get the plotting automated plotting for the zombie thing? Like working so that the graphics programmed by Zen work correctly by default?
Yeah.
Yeah.
That's what we were doing in the workshop, right?
Yeah, I guess we think correctly.
Is this like an acorn that turns into an acorn that turns into a tree? Now I'm excited. I'm excited for what could potentially
Grow later.
it totally grows into a tree and then dies. I'm just guessing by the
Totally grows between a what? What?
I started as an acorn and then grew into a tree. And then it would die.
Because maybe you can start with something, but then
In English.
They're all very good questions, you guys.
at least game of life.
Okay,
That's like huge.
I'm expecting it.
here we go.
I don't know if it's a tree or not, but
That's interesting. We've got those blocks of the stable.
Yeah.
The key is that they're eventually going to die.
no, I think this is just an evolution thing where
So those are stuck, and then we can get, we see a lot of spaceships, gliders. Okay, we see a lot of oscillators with blinkers here. Here, this is another stable pattern. These all have names. Like this is toad. Okay, but from that little seed, from that little acorn, is growing this magic tree.
I see.
So I have no idea why it's called acorn.
I think because it just creates stationary states that eventually get acted upon where they create more moving states.
So at this point, we're probably off of the actual acorn trajectory because we may have wrapped twice here at boundary conditions. Probably right.
Oh, interesting.
Yeah. So even with 1,000 by 1,000, which seemed ridiculously big when we started, it sounds just.
We also start to write in the corners. That,
Doesn't
Doesn't
matter.
matter.
We're at a boundary condition.
yeah, that's right.
Neat.
Yeah, that is really cool.
Okay, so super simple rule set, we can get really complicated stuff happening. Let's look at one more. Oh no. This one is actually an infinite growth. This one never dies
No, I thought we took over the
or
whole.
goes stable.
So infinite growth also suggests that we're turning more cells alive than they are dying. But on any kind of, I guess they don't assume this is why we do infinite size grids.
Yeah.
Because if you do any finite size, and you eventually start
So again, we're going to have those artifacts creep in here, but let's at least see what happens.
Yeah.
So notice it's interesting because you can have stable structures that are then hit by these spaceship structures. Totally changed. This guy was a stable structure and then it got hit, and now it's an oscillator. Now it's destroyed. There's a glider.
This is how quantum gravity works better.
It seems
Yes, exactly. This is my bottle of quantum gravity. Don't you understand?
it seems kind of cool how like you can have these crazy kind of geometries going on, but there's when a pattern is in a very specific configuration, you know exactly what the next step is. So you know you're going to get like a 4 square stable. You know you're going to get a spinner. You know you're going to get like a glider that has a very specific shape.
Yeah, but then look, we just had like a little glider come here and hit like 1 or 2 blocks, and that whole crazy pattern emerged.
Yeah.
It's deterministic, but it's extremely low.
Yep.
Which is probably actually have quantum gravity. you know, so we've got simple rules that. I mean, so this is like, if this is our underlying world, right? It actually becomes more viable to talk about things from the emergent structures than from the underlying. So even though the cells are more fundamental, the structures are more.
It's too hard.
So you guys are asking good questions, and you have a pattern that's basically like self-replicating. Okay, and you have something that generates things continuously. Okay, so this was a long-standing question for a long time, and then someone answered it. Very famous solution. Gosper is the one who did it. Gosper's glider. So this looks like
Something special between regular gliders and Gosper stuff?
what's more, Gosper's glider gun.
So we're going to hit periodic boundary.
Legend. That is totally cool. It's a very pleasant surprise.
Starting this weird crazy shit.
That initial condition is Gosper's glider.
So two stationary objects and two objects that are equal with the transitional motion.
Cool. Guys ready? Shooting out gliders.
That is
Whenever somebody asks you, what do mathematicians actually do?
We shoot spaceships.
that's really cool.
Neat, hey?
Oh, it's gonna.
Watch what happens. Gun dead. It killed itself.
And it leaves just this constant stream of gliders.
This is a lesson. Never shoot bullets away from you when you're on a donut. It's not gonna end well. Cool, hey? Alright, so simple rule set, simple initial conditions, we can get really complicated things. Alright? So that's the game of life.
Somebody really had to be playing around with that for a significant period of time in order to see something like that. Like short of the computer generating pattern where it knows it's trying to get something.
Well, there's techniques for this kind of work, right? So, like, you would probably set it up with a given domain size and then randomly generate a condition, write a code to analyze the output that doesn't make a mistake. Experiment.
So
That's
there's
just-
something interesting about this. This seems simple, but we see we can get complicated stuff, right?
just
We can
moving
get
those
oscillations, we
things
can get
back.
stable patterns, we can get this like infinite generation of certain sequence. So the question is, well, exactly how complicated can this get? And the way of rephrasing that question is, can this get as complicated, theoretically, as any computational engine? Okay, does everybody know what I'm trying to get at? There's a certain criteria.
Oh, very complete.
Turing complete. Okay? Does anyone besides Martin know what Turing complete means? Want to guess? Something's Turing complete.
That the thing where there's something to
No, that's the Turing test, right? For AI.
Yeah, Turing tests
Yeah.
are like AI is like I think I know that one, but Turing, I guess.
I've heard want to guess.
I've heard it.
Yeah. Martin, want to guess?
You can basically write any program that can do it in a Turing.
Exactly. Okay. It is of sufficient complexity. It's able to do enough operations that any calculation in theory can be done. It may take a ridiculous amount of programming and be ridiculous in scope, but in theory, it can happen.
Like how people have written or have built computers in Minecraft.
Yep, Minecraft is Turing complete. Okay. basically there's block types in Minecraft that allow you to do logic gates. And if you can do logic gates, you can build a game. Okay? The game of life is Turing complete. You can actually set it up so that you can get those logic gates. Okay? I don't suggest you do it as a way of calculating your next research problem. Okay? But that's just to show how, even with these simple rule sets, just how complicated it is. Okay?
If we wanted to do an infinite domain in this case, I think it might be better, given the rules we have, to just say that all the boundary cells are dead. Perfectly for library.
Yeah, so that's like an example of a different, but I mean, then nothing will ever escape your box, right? So an infinitely growing pattern would die at the edges of your box.
Right, so it could die locally and still be existing.
Exactly.
Yeah, okay.
Cool. Okay, we're going to look at other examples. And one of the examples we're going to look at will explicitly show how we can make logic gates. Okay? Before we do that, just because they're cool, let's go through the list of cellular buttons.
Rule 30 was just a gigantic block of stuff.
We're going to talk about Rule 30 in detail.
There's actually.
Yeah, and they're really interesting. Brian's brain. This is a 3-state system. On, dying, or off. Okay? And this is typical of what cellular automata simulation does. It's very dynamic, a lot of sweeping patterns. There's all different names for this. You can read, there's like rakes, and the rakes generate spaceships. Okay?
It's like maybe
Yeah, so we'll get to those ideas in a little bit, like kind of like, well, this is all pretty, but what can we do with it? Okay? And so Brian's brain is another one of these, like Conway's game of life, that is kind of like a canonical example of this that can then be used in different contexts. Cool? For example, modeling neurons.
Well,
Brian's
the
brain.
ecology simulator that we had a presentation on a few weeks ago looked awesome.
Yeah, that was basically cellular automata. Yeah. Well, it was cellular automata. Just more rule sets.
Yeah.
More states.
And they are calling this one chaos.
Yeah,
Yes, cellular automata can be chaotic.
I imagine having 3 states of doing this in 3 dimensions and making it just overcomplicate things.
Well, we're going to come back to that question later. Okay.
So Conway's game of life is this sort of rule set?
Yeah. Well, a couple things. It's a rule set and also the stencil, so the 4 neighborhood, right?
Okay, yeah.
And it's in 2D. And it has 2 states alive and dead.
Okay, and these starting configurations generate spaceships, different starting configurations that people come up with
Exactly.
under problems.
Yeah, precisely. Cool. Okay, that's Brian's brain. What are some other examples? Langton's ant. Okay, and this is one that can produce regular patterns, or I'm not sure if they're chaotic. Let's see. Yeah, chaos. Okay. So there's kind of 3 distinct modes here: simplicity, chaos, and emergent order. Okay. And so what is ant? At a white square, turn 90 degrees right with the color of the square, move forward 1 unit. On a black square, turn 90 degrees left with the color of the square, move forward 1 unit. Okay? So you can visualize it as this ant moving across the surface. Okay? And it makes these decisions. Cool. Pretty simple rule set. What do you get out of it? Well, chaos. Nice ordered pattern. And then they talk about, this is a convoluted highway, spiral growth. Okay, so you can get really complicated motion. Neat.
By changing whether it turns left or right. Is that what the RLR? Oh yeah. That's
So
what
it's extensions to multiple colors. Yeah. Yeah. Cool. These are what just the basic algorithm looks like. You can get these ordered type of structures, but this is the highway, and then this is the chaotic pattern. Cool. Again, super simple rules into really complicated stuff. Yeah. Wire world. This is neat. So I want to talk about this one, and then we'll look at simulations.
Some more important.
Okay, we're going to have 4 states. Okay, we're going to have empty. There's going to be black. There's going to be 0. Well, I'm not sure about these colors. So empty is going to be type 0. Okay, state 0. Wire world, we're going to talk about electrons moving. Okay, there's going to be an electron head. You're going to have state 1. An electron tail. You're going to have state 2. And we're going to have a conductor, which is state 3. Okay, so these are our states. We can use a Moore neighborhood. And of course, what we need is our rule set. Okay, empty goes to empty. Okay, electron head goes to electron tail. Electron tail goes to, any guesses? Conductor. And a conductor goes to electron head if 1 or 2 neighbors are electron heads. Otherwise, conductor.
What's the point of it?
Pardon me?
What's the point of empty?
Yeah, exactly.
To create wires. You know, electrons moving into emptiness.
So here's our system. Basically, we can just ignore everything that's empty, or there aren't conductors or electrons. We can have some path. Okay, there's a path. This is all conductors. And what's going to happen if I put an electron head here and an electron tail here?
Start shooting. We hope
Which way?
electron head goes to the tail. And the tail moves.
So
So
this
and
becomes this. And this, because it has a neighbor that is an electron head, is an electron head. Right? And this becomes conductor again. So it just moves forward. Cool? The electrons flowing out. Cool? Cool. So let's look at how we would program this. We have anything here. 3 is, this is head and tail, right? Let's see. Ooh. Okay, so here, well, let me find this code. Let me try something. Okay, so here I have no idea why I put these here. Okay, get rid of them. But basically, this is all conductor here, and red is empty space. This is an electron head. Okay, so this is just to show the motion we just showed. What we end up with is electrons passing through the system. Okay, I also have a clock in my system to generate electrons here. That sounds great.
So it's not periodic.
It's not periodic.
So you don't actually need a tail. Like your first initial condition is a tail.
No, it makes a tail because the head goes to a tail.
Yeah, exactly. So you don't
Yeah,
actually
you don't need a tail. Cool. So here's the code for that. Okay. This is what, I don't know why this isn't there. Okay. So I'm basically turning everything to be off. And then here I'm laying down a strip of conductor. And then here, right, I'm setting it to state 3, which is conductor. And I'm only doing it for a specific J value, but for all i's. Cool. Yeah. Yep. And then here is where I just put in the electron head. And that's it. Here, I have a periodic electron generator. Okay, so that we can see electrons flowing through the system. But with most cellular automata, we just want to let it go. Watch what happens. We don't really want to do this time-dependent messing with the system. Okay? So, is there a way that we can actually have wire world generate electrons at some fixed frequency from the internal loops? Okay? And this is called a clock generator. All right. Exactly.
Maybe we can mini generator.
You have a loop, and this, right? And when the electron head comes around here, the conductor, this conductor says, oh, I have a neighbor that's electron head. This one says, oh, I have a neighbor that's head. So this electron continues to go this way, and it also shoots one out this way. Yes.
Doesn't matter, it's a generator. That's the point.
Cool. This is a way we can, and then of course the bigger the loop, the lower the frequency of electron. Cool. So this is a way we can have a clock. Cool. Is that good with you guys?
What's the rule if a conductor has 3 neighboring electrons or are we using more neighborhoods?
Yes.
We have more than 2.
That's a good question.
They cancel it.
I think they cancel out.
Yeah.
I think it's only for 2 or 3. Yeah. Okay. What does that code look like? That looks like. I'll go to the bottom again. The huge folder. A lot of programming goes really nice. Okay. So what I'm basically doing is making a loop here. I'll show you the. Let me show you the results first. Okay, so there's my loop. I have 2 electrons going around this one, and we'll see why. Okay, but we don't need 2 in there. And so that's what's going to happen here. Very fast, we'll slow it down. It just looped. Okay, so whenever it comes to that end of the loop there, it shoots out an electron and also keeps moving around. This is how we can periodically produce electrons. Cool? Okay. Now let's see how we can actually do this, perform logic operations. So I think this answers Martin's question. It must cancel it. Okay. So let's look at this. You guys know what an XOR gate is? What is it?
You've got 2 inputs, and the output is produced if precisely one of them is true. Yeah.
Yeah, same thing.
Yeah, same.
Exclusive.
Okay. So 2 inputs, and or one of them must be 1. And it's exclusive OR because if both of them are 1, it produces 0. No. Cool. So an OR would produce 1 if both are equal. Exclusive OR produces.
So in order to get something like this, we have to be able to exploit the construction of conductive 1. So we should have like a changing shape inside of it.
Like, are you talking about like building this in real life?
No, like when the simulation goes, when a head goes to a conductor, it should be in such a way that we should be able to create conductor or remove conductor from. Can we?
No, you want to lay down a track of conductor.
Yeah.
That has 2 wires leading to it and 1 coming out.
Private, the exact same. Way too fast. Okay, and so they produce an electron.
Wait a minute. Oh, wait, because the head goes to a tail, so that cancels out leading and the last tail.
cool.
It's really cool videos.
You guys all right with this?
Mhm.
So those are ones that are close together, but not at exactly the same time. Okay? I gotta remember how to do this. This is where I set my electrons. Yeah. Here we go. Okay, so these are slightly displaced because this one's at 4, this one is at 5. Okay, so let's see what happens. Make them exactly synchronous. Oh. Destroy each other. Okay, so exactly synchronized, no signal gets.
So is this sort of thing used to simulate circuits specifically?
Yes, but no. Yeah, there's actually quite a bit. There are like wire world packages to help you set up wire world cellular automatic. Yeah. But in terms of serious circuit design, I don't think so, but I'm not positive.
Yeah, it doesn't follow up in the same. Other than being
That doesn't never stop people. The point of this was to more show you how cellular automata, simple rule sets, can be used as logic gates. So they can be used as logic gates to make a computer, right? Just like Minecraft. Cool. That'd be cool. And of course, you can get into the complicated ones. So if we go back into this.
You know, imagine people have made like ridiculous systems.
Okay, and so here are your diodes. They only go one way.
That's so cool.
Okay.
So you have like gates, diodes, and
So in this sense, they can be used to model circuits because you can build all the components.
Yeah, that's what I was thinking.
And wire world is Turing complete, as I hope I just demonstrated to you. And they, of course, can get really crazy. You can use it. It's pretty nutty. Very complicated circuit here. And eventually we should see the number 9 light up on this.
What's that they're doing? 0. So they just form that baseball.
Exactly.
There's no geometry.
No.
Oh, it's all conductive.
No, no, no. There's conductor. Yeah, wherever there's green, there's conductor.
I can't. Yeah, you can't see green.
Yeah.
I thought they were
There's
just-
definitely conductor. But you can't just do wild world.
Yeah, yeah.
Oh, yeah.
Oh,
Wire world.
Oh, okay.
oh, I see. Okay. I thought they were just interfering. I mean, you could do well an alt conductor.
They get pretty nutty.
you should use light that creates conductor, and then the wire will act on it.
So does this simulation, I don't know if you know, but did they set it up so that you could change the inputs to light up different numbers?
That I don't know, but
Because that would.
Set a 7-segment display and
Yeah, so you can specify ahead of time how many you're
Yeah. We'll create display.
Here's our XOR gate.
Oh, there's the.
Yeah.
Well, I think that's different design.
The power to, no, it's the same
Oh.
one.
No,
No, it's a different one. That one's showing 9.
But depending which bit they turn on, that's
No, like it's
That's
the
a
same.
decimal
It's the same
divider.
pattern, but depending on which one you turn on at the very bottom, will tell you what shape you're going to get at the top.
That's probably true.
So if we turn on a different one, we get a different.
yeah. There's 9 things at the bottom. So that whichever one you send a which one it lights up.
Cool beans. Cool beans. So this is just an introduction to cellular automata. Next class, we're going to start going through them details, starting with the elementary cellular automata. We'll look at a couple of systems. Okay. Great. Cool.
And they say people don't have free time on their hands.
And there's a lot of research into this, man.
are there
Research that uses cellular automata.
are there systems where you can model real world stuff? Because a lot of this is like leaving back to the world. Here is the
No.
world.
So we're going to start talking about that next class. You can actually do very simple traffic simulations using cellular automata.
Right.
Yeah, and other stuff too, right? Like they're talking about that